my topic today will be about the use of satellite in grazing system and how those models can be used to support decision support tools, decision support tools. So this presentation is divided in two parts. The first part, just to know, I'm a nutritionist, ruminant nutritionist. Then I just share with you some learning about the topic. Then the first part of this topic, I will get a brief overview about the grazing system and the problem you wanted to tackle with satellites, and a little bit about the satellite system also. And the second part, the core of this presentation, where I talk how satellites, I don't know. Satellites can be used to monitor pastures and how those models can be included in a decision support tools. So let's start an introduction. Well, for those who are not ruminant, the grazing system, it's a complex plant, animal, and soil nexus. To establish some control over those grazing systems, we set some grazing management, and to get some data or metrics for these grazing measurement techniques, it's important we monitor those grassland biomass, the grassland forage biomass production. So the conventional techniques for measure these grassland forage biomass is based on ground measurements. Although those ground measurements are user-friendly, or they are very used or very easy to use, they has limited assessment of the spatial and temporal variability of the forage production throughout the year. So the satellites emerges as a technology that we can monitor remotely from small to large areas of grasslands. And the most important, the satellites can assess the spatial and temporal variability of those forage production. So how does the satellites work? I will talk here about the Earth observation satellites that are the satellites that we use for agriculture purpose. Those satellites carry sensors, and those sensors has the principles and functionalities based on the electromagnetic radiation. That means that I can use the satellites to forage production in agriculture because every feature or object in the Earth's surface interact with specific wavelengths of this electromagnetic spectrum, and they result in a unique spectral signature. Then here I give you some example of the typical spectral signature of a healthy green vegetation, a dry vegetation, and a soil. And you can see that each one has a unique spectral signature. So the visible, this is a nice curiosity, the visible spectrum, that means the spectrum that our eyes can see, it's a narrow one for approximately 400 to 700 nanometers. And in terms of vegetation, green vegetation and greenness, the two wavelengths are very important, two spectrums on these wavelengths, that is the, how can I, that is the red one and the near infrared one. How can I point here? Sorry. This one? No, I think it is this one. That is related. sorry. Anyway, it's the red spectrum wavelength and the near infrared spectrum, wavelength of the spectrum. So how can I use the data? What is the data, the input variables data from satellites? In this case, I'm just talking about the satellites with optical sensors. You can use the spectral reflectance of a specific range of these wavelengths of the spectrum, and you call those bands. Or you can come up with some vegetation indices that are mathematical formulas or algorithms that relate this spectral reflectance from 2 or more bands. The most, oh my gosh, something get wrong here. The first one is the NGVI, that is the most usually and used vegetation indices for agriculture or greenness proposed in agriculture. Actually, this NGVI is the stands for normalized difference vegetation indices, and this NGVI is a normalized difference between the near infrared spectrum and the red spectrum. The other ones is just to illustrate that we have some other greenness vegetation most used, like the enhanced vegetation index, and some soil adjusted vegetation indices for sparser area or for measurement of soil conditions. So the important thing is not all satellites are equal. And depend on the satellite that you use from your model, the data from the satellite you use from your model, you have different performance and results in your model. So the satellites basically can differ by the domain. We have some public satellites, or those ones that are free. You can get the data from free. Or you have some commercial satellites that you need to pay for get the data. The satellites differ from themselves based on their sensors that they carry. Like the sensors can be a passive sensors that the passive sensors that they depend on the sun radiation. Is the optical sensors that I've been talking here in this presentation. But the sensors can also be an active sensors. They have the own radiation power, source of power. Then the most used are the radar or LiDAR sensors. The other resolutions, thank you for Dr. Temi about sensors. Satellites carry sensors, and those sensors have resolutions. And depending on those resolutions, you can use the satellite for a specific use. Here you have the main resolutions that we need to seek when you talking or choosing satellite. That is related to the spatial resolution that is the minimal pixel size or the minimal area that the satellite can collect data. The temporal resolution that is related to the time that satellite revisits the same area again. The spectral resolution that is related to the range and the number of wavelengths that the satellite can capture, the reflectance. And the radiometric resolution that is related to the beam depth or how many levels of intensity one pixel can capture in an image. And here is some examples of those resolution in some satellites. So how does satellites can be used to monitor pastures? Indeed, we have several applications for satellite data in cattle production. Herein, I will talking about 3 of those applications. That's regarding to land classification and map, the estimation of biophysical parameters, mainly related to estimation of biomass, forage biomass, or the estimation of chemical parameters, like nitrogen or fiber content of forage. So, the models for land classification and mapping of grasslands are mainly based on machine learning models. They can be unsupervised, in this case, when you don't have a graph truth measurement. Then the most used one is the PCA, the principal component analysis or cluster analysis. All those models can be a supervised one. Then I will show here 3 examples of those 3 papers that use these models to classify and how you use these satellites to classify. In this first example, the author used the mapping, the land use intensity of grasslands, used the Sentinel-2, the time series. Look that every paper you need to look up which satellite the authors use. In this paper, the authors aimed to mapping graze intensity, mowing frequency, and fertilization, if the pasture or fertilizer or not with nitrogen fertilizer. And they test 2 models, the convolutional neural networks and the random forest. In this paper, the author the author concluded that CNN are better than the random forest, and they could classify the area with a precision of 66%. In this other example, the authors use Google Earth images. Actually, the Google Earth, we have a very useful tool to get those images, that is the Google Earth engine. Then in this example, the authors use the Google Earth engine in a large-scale monitor of bush encroachment in South Africa. That means the author wanted to see the areas with wood or no wood areas. Then basically the authors get these images, then they calculate some predictive variables and determine the training and training pixels. They use the random forest to perform this classification, and a graph through measurement to validate this classification. And they apply this classification, this data set, in a large scale satellites like the Landsat and MOOCs. So, the authors, this is the result of this data, this paper, where you can see that the authors show that for 2 places, the example 1 and example 2, the model could perform this classification with high reliability, but in the example 2, in the place 2, with a moderate reliability. In this, I just wanted to show you some examples of coding in the Google Earth engine that I've told you about. It's a cloud-based platform where you can get some images, satellite images, and then work of those satellite images. Here, I want to just to show you that as we are working, in this case, with optical sensor and they depend on sun radiation, they also have some interferences of the cloud and shadow. And satellites are sensors. So to use their data, their final data in their model, you need to perform a lot of corrections, and one of those corrections are related to the cloud and shadow of the areas. And in this coding, we use random forest classification to classify the areas. This is regarding types of vegetation and soil background. So the other use for satellites, the use of satellite in grazing system is to estimate these these biophysical parameters that right now I'm focused on estimate the above ground forage biomass. So the general assumption is that if I have the spectral reflectance and the vegetation indices, these are able, they can differentiate vegetation from soil features. And most important, my general assumption is that a denser grass, that means the amount of grass, the forage that we have in their area is related to the amount of the visible light and near infrared energy that a pixel can capture, the value that a pixel can capture. So to estimate these biomass, above ground forage biomass, you can use mainly is based on the correlation. Based on the assumptions, we do a correlation between this above ground forage biomass with vegetation indices or spectral reflectance. The models that you can use are regression models, the beginning of those regression models. Then we evolve to machine learning models, and to evolve on an integration, using an integration of those satellite vegetation parameters and biophysical models. Just to have a general idea of flow chart of how these regression models, this is a simplest way of a flow chart to exemplify how our regression models can be built. The first point is we need those models. Usually you need a growth truth measurement to validate these models. Those ground truth measurements are connected with the satellite data measurement, the spectral reflectance, based on a geoinformation system and a date that you collect those measurements, both from ground truth and satellite. Usually based on the spectral reflectance, we come up with some vegetation indices. You calculate, estimate vegetation indices, and you perform at the beginning, usually you perform a correlation analysis between the growth truth measurements, basically the epsilon part of the model, the variable, the dependent variable, with those vegetation indices. Then I can come up with the vegetation indices that is highest correlated with those measurements, forage, in this case, the forage biomass. So you select the variable, the vegetation indices, and you perform the regression model and evaluate these models based on the evaluation parameters that is very known. So I come here, I just bring some examples of how this regression model works. And I bring actually examples based on warm season grasses and legumes and tropical forests. For warm season grasses and legumes, what you can see, every time I say that I'm work with satellite, the people asking me about the NDVI. NDVI is the most known and used vegetation indices regarding this agriculture, this greenness. But indeed, they work well with warm season grasses and legumes, but in a non-linear function, basically because the NDVI has a saturation, they saturate above 2.5 leaf area index when you have a more than 2.5 leaf area index. Those regression models has a precision between 50 and 70%. And but for sparse areas, the best one are those soil adjusted vegetation indices that result in better correlation. Those models are able to collect this variability, this temporal variability of the forage production, but they always call site specific. In terms of those regression models for tropical grasses, the papers have reported that you have a poor prediction of above ground dry biomass, forage biomass, mainly because the structural components of those forage grass and the high content of the senescent material on these forage pastures. So the best predictions based on regression models are based on a linear relationship between the vegetation indices and the green or leaf above ground biomass. And besides NDVA, the other vegetation indices have worked better, like the EVA or the some soil adjusted vegetation indices. It's just to illustrate the results. So since 2015, we have exponential development in information technology, and with the machine learning models and the increasing of machine learning model adoption. And in our case, related to satellite and the amount of data that we can come up with this technology, we evolved to the use of machine learning models. Usually, the machine learning models in the satellite images are based on a supervised learning, because you need a training date based on the ground measurement to validate those models. And one of the great advantages is that they can circumvent multicollinearity problem that is inherent to the satellite data that you can acquire. For instance, here, it's a heat map between among the satellites reflectance bands, the spectral reflectance bands and vegetation indices. As you can see, the spectral reflectance bands are highly correlated themselves, as well they are highly correlated with their vegetation indices, because the vegetation indices use the spectral reflectance to calculate, to estimate. So here is a briefly simple flow chart, a general flow chart of how you can build those models using machine learning to come up with some above ground biomass or forage biomass, or even further to chemical parameters. Then the first topic is that similarly to the regression models, you need the ground truth measurement and the satellite data, like the spectral reflectance. But in this case, because the machine learning models can hold a huge bunch of data, the input data set, future data set, I can use in this input data set the spectral reflectance, some vegetation indices, then I can calculate together with meteorological and topographic data to improve those models. Then the other part is very now for data size. The important here is not to forget to normalize the data, because the data has a lot of the differences in units. Then you can select and compare your models. So here an example of how those machine models can be used to predict these above ground dry forage biomass using Sentinel-2 images. In this case, you have a large area. The authors use large areas. The flow chart is very similar for those ones that I've shown you previously. And here is the model validation. Then you can see that actually in these papers, the author used several regression trees types of machine learning, but the random forest was the most precise one. The other way that you can use the satellite in grazing system is to estimate the nitrogen and the fiber parameters. NDF stands for neutral detergent fiber. That is a chemical parameter from forests. Usually, those previously, those chemical parameters have been estimated based on hyperspectral sensors in the laboratory or those sensors in the field area. Because the hyperspectral sensor, they can capture the wavelength in 100 wavelengths. It's more sensitive, based on laboratory high spectral sensors. Then, but with the Sentinel-2, the launch of Sentinel-2 from the European Spatial Agency, this Sentinel-2 is a free source satellite that can measure the narrow bands between the red spectrum and the near infrared spectrum, and we call those between those regions the red edge regions. And those red edge regions of Sentinel-2 are able, they have been shown to be able to capture this variance in nitrogen and fiber content of forage grasslands. As you can see in this example here, this is a graphical example where the authors compare the Sentinel-2 with two spectrometry from field and from the laboratory, and they concluded that the Sentinel can be used in those models. Usually those models use machine learning algorithms because you need to, the input features need to be all the spectral reflectance. And I expect by the end of the year, we have some data regarding tropical forests. So this is an example of a website where we can apply all those data from these models. You can apply in a web, in the clouds, platform data, and they can translate this to the forage amount of how much forage you have in an area. So we have a next step. With the satellite imagery, I hope by now I could prove you that you can use the satellite image to predict forage biomass or chemical composition. In terms of agriculture, this would end here because the end product of soy, bean, or corn, or etc., is the plant. However, in livestock production system, the forage is just one part of the equation. The forage is related to the feed supply. It's the part of the animal will eat. How can I connect then those data from the satellite images, the forage biomass, with the animal part and come up with a model that can be used to translate this forage mass in a decision support tool? We can do this connection between the feed supply with feed demand by the animal. We can connect this through several ways. In this case, I'm connecting this feed supply with this feed demand based on the forage allowance. That is a metric that measures the amount in kilograms or pounds of forage mass that you have in an area to the with the how much forage you have per kilograms or pounds of animal in that area. Because the forage allowance has been reported to be related to dry matter intake of those animals and the animal performance. So this is an overview of this model. This is the decision support tool models where I can connect the part of the feed supply with feed demand based on forage allowance, carry capacity, and to come up with the amount of supplementation that I need to supply the animal based on the productivity, profitability, increase productivity, increase profitability, and mainly decrease the environment impact of those production systems. So this is a conceptual model or decision support tool when we connect all those information about the available forage with the part of the animal, the herd size. In this case, is a cow-calf grazing model because this model was built to optimize weaning weight, profitability, and sustainability of the grazing cow-calf operation, because we seek for the best producing weaning cows based on the herd size and the forage available forage. So we connect all the available forage that you can estimate it based on satellite image, and those satellite images can connect all these variability throughout the year. We connect this with all the ruminant nutrition system, the mathematics and regarding to animal requirements to come up with the best result. Actually, we do a simulation of this model, and we are presenting a poster regarding this simulation. So in summary, the satellite-based remote system is a feasible, reliable, and resourceful technology to monitor grazing areas. Basically because they can capture the spatial and temporal variability of the land. They can be used from small to large areas, to small to global areas. And one of the great advantages, you can use the historical data. You can retrieve the historical data to build a model. Moreover, the ability of the satellite-based data to quantify or to be used in vegetation characteristics depends on the type of the sensor and instrumentation features of the satellite. So to build a decision to support tool for sustainable grazing system, is perfect feasible if you can join the satellite-based forward models with ruminant nutrition models and environment models, and contribute to support precision livestock farming.